Hello and welcome back to Chem 4 lecture. We have finished chapter 4 and now we are starting chapter 5 with today's lecture, which is all about nuclear chemistry. Now, there's a lot of material in the nuclear chemistry chapter that you're going to be asked to do on the homework, but you're not going to be expected to do it in the test. So I just want to kind of lay that out up front. You got two lectures here for chapter 5, lectures 9 and 10. I'll walk you through how to do those problems, but you won't need to commit that to memory. I want you to have a little practice. That's why those questions are on the homework, but they are not going to be on the test that we have coming up. So, yeah, okay. So, and the reason for that basically is that for you going into the health field, which covers most of you, and then those of you who are just here as a take this as an elective, nuclear chemistry is interesting for a variety of reasons. One is that a lot of times different imaging techniques require the consumption of radioactive material that then locates itself somewhere in your body that then shows up on an imaging screen. Like, for example, when I had to get my thyroid or the area, or sorry, I guess it's like there was a thing in my neck around the thyroid, and in order to light it up, what they did is they gave me an iodine drip that contained a radioactive iodine. And the thyroid is where your iodine goes to. So the iodine concentrated there, then they were able to image it in an MRI machine and actually see, the area around the thyroid from that. And that's true with, there's a number of different radioactive materials that locate in different areas in the body. So depending on what you want to image, you may take a different radioactive material. Also, of course, there's a chance like you may be exposed to radioactivity. And in that case, that has serious consequences for your health as well. And so, hopefully there's no like nuclear bombs blowing up and, dealing with radiation poisoning. But who's to say it's not impossible that someone could have issues with radioactivity sometime in the future that, you need to treat. So we want to understand what radiation is. In order to do that, we're going to explore the reactions of the nucleus that we call nuclear chemistry. Okay, so basically radioactivity is, there's high energy particles that are emitted by unstable nuclei. So when we talked about the nucleus before, we mentioned that it's where the protons and the neutrons are in the atom. And we looked at like stable isotopes, right? Where, you have different numbers of protons and neutrons making up stable atoms. Now, not all combinations of protons and neutrons are stable. For example, carbon-14. So carbon-14 has, of course, 6 protons in its nucleus and then 8 neutrons in the nucleus. This arrangement basically has too many neutrons in together with the protons for it to be stable. So it's going to undergo radioactive decay. So that's what we're going to talk about here with section 5.1. Okay, so the naturally occurring, so most naturally occurring isotopes of elements up to Z equals 19 are stable. So they have stable nuclei. You don't see many that are radioactive at that level. But elements that have atomic numbers 20 and up usually have one or more radioactive isotopes. And again, these radioactive isotopes just have combinations of protons and neutrons in the nucleus that are unstable. So this unstable nucleus is what we call radioactive. In other words, it can decay and change the number of protons and neutrons in the nucleus. It emits radiation, what we call radiation, in order to become more stable. And there's different flavors of radiation that we want to be able to understand. So radioisotopes. A radioisotope is exactly what it sounds like. It's a radioactive isotope. In particular, it's an unstable nucleus. Again, it decays and it emits radiation. There can be multiple radioisotopes for a given element. And as you go up the periodic table, the more likely you are to hit radioactive isotopes. And you're always going to include the mass number in its name. Now, I mentioned this is one way that you can write down the mass number, the name of the element followed by the number, the mass number. Like carbon-14, for example, we know is carbon that has a mass number of 14. Since carbon has atomic number 6, that means it has 8 neutrons. So this is our normal way of writing it, but we can also write it this way, name followed by mass number. Okay, so let's look at some of the radioactive isotopes and see, just kind of compare some of the different nuclei that are out there. So I mentioned iodine already. Iodine has a stable isotope, which is iodine 127. In other words, iodine 127 does not undergo radioactive decay. However, there are two, iodine 125 and iodine 131, that do undergo radioactive decay. So these are unstable nuclei, and these are what we would call radioisotopes. Magnesium, on the other hand, so magnesium also has a stable isotope, that's magnesium 24, and then it has two unstable radioisotopes, magnesium 23 and magnesium 27. Just by moving around the number of neutrons, well, the number of neutrons will make the isotope, the nucleus, unstable, right? If there's think about it this way, basically. If we look at the nucleus again, if there's too few neutrons in the nucleus, then the positive charges of the protons are too close together. And of course, we know positive charges force each other away, right? We repel. So we would expect that to be unstable. Adding too many neutrons can also be unstable for a different reason, which gets into, why is the nucleus held together, as far as the weak force of the nucleus and the strong force of the nucleus, that we don't have time to explore. But just rest assured, the wrong number of neutrons, either too many or too few, will lead to an unstable nucleus. Finally, uranium. Uranium is atomic number 92. There are no stable isotopes of uranium. All uranium will undergo decay. The only question is, how fast does it undergo decay? We have uranium-235 and uranium-238. Uranium-238, I know, has a half-life of billions of years, so it takes a long time to decay. Uranium-235 is much quicker. This is the actual fissile material that's involved in, the most common form of nuclear power and the most common form of nuclear weapons. Okay, so this is the types of radiation. Now, we're going to explore the types of radiation, and you will be expected to know the definitions of these and their, the potential dangers of them, as well as the penetrating power. We'll talk about that. But we will not be expecting you to do the balanced equations that we're showing later on in this chapter. So let's go ahead and talk about this. Now, alpha particles, if you are a keen eared listener to this lecture, you may notice that we already talked about alpha particles because we talked about them when we talked about Rutherford's gold experiment, where he discovered the nucleus of the atom. These alpha particles are basically a helium nucleus. And I don't have my writer here, but this should have like a 2+ charge. So I guess I can annotate, even though it's not as nice. So this has a 2+ charge because it's a helium atom that's been stripped of its electrons. So it's just the nucleus here. And yeah, that's what we call an alpha particle. Then we have beta particles, which are just high energy electrons. Now we write the beta particle like this, where you have E0, and then down here, -1. Now, why would we write it like that? In the past, we've talked about electrons like E, and then sometimes when we draw in the charge, we'll draw in a little minus sign up here. Well, the reason we have this minus sign is because it has a negative charge, a -1 charge. Well, let's take a look at what we have here. We want the electron to represent something in a nuclear equation. And in order to do that, we know that it has 0 mass. In other words, there's no proton or neutron in an electron, right? So electrons effectively have 0 mass. That's why we have it as a 0 mass number up here. The -1 atomic number just relates the charge of the electron. So think of it this way: an electron is like -1 proton, right? Because a proton has a +1 charge, the electron has a -1 charge. So if we're trying to write an atomic number for an electron, it'd be -1. Okay, so that's a beta particle or a beta minus particle. There's another type of particle called a positron, and this is a beta plus particle. The positron is very similar to the electron, except for 2 regards. So it has the same mass as an electron, but it has the opposite charge. It's got a +1 charge. Also, if a positron hits an electron, they annihilate each other. So these are what's called antimatter. Positrons are a type of antimatter. And not to get too deep, again, this is beyond the scope of this course, but if you're curious, of course, I can talk about it more. And you can always just look up the Wikipedia article for antimatter. And, if you're like me, you'll be fascinated for a while anyway. But every particle of matter has an antiparticle. And the antiparticle of the electron is the positron. And if a particle and antiparticle meet, they annihilate each other and produce energy that's released in the form of photons or light. So that's what a positron is here. You may have heard of positrons before because they're involved in positron emission therapy or PET. We are going to be taking a look at that soon. And then finally, we have pure energy gamma rays, and these are just high energy photons. Let me put that down here before we forget. Gamma rays are just high energy photons, and they're at the very short end of the scale when it comes to wavelength, and they have extremely high energy, and they are extremely dangerous. Okay, so real quick, let's go ahead and talk about each of these in turn, and I'll show you how to do the equations, but again, those are going to be on the homework, but not on the test. Okay, an alpha particle is identical to a helium nucleus, so it's a helium atom that's had its 2 electrons stripped away. So it's just, you're left with a tiny, tiny nucleus that has 2 protons, 2 neutrons. The mass number is 4 because 2 protons, 2 neutrons, mass number 4. The charge is 2+ because it lost both of its electrons. And this is a very low energy type of radiation, but potentially very damaging. Let's see. So I guess we don't talk about here, or I think we're going to talk about how to, okay, here. Okay, we'll talk about this in the future, how to protect from the radiation. Sorry, wanted to make sure I had that there. Beta particles, these are the electrons, and it's just a high energy electron that's emitted from the nucleus. And what happens in beta emission, so the emission of a beta particle, this occurs when a neutron flips into a proton and an electron. So the proton stays in the nucleus as the neutron changes, but the electron is emitted just to balance the charge, number one, and then also release the excess energy and matter that's there. So this is why if you, this is one instance where you can have, this kind of explains why a neutron is heavier than a proton, because neutrons flip into protons and they produce an electron. Positrons happen the opposite way. A proton can change into a neutron and a positron, and this involves basically either the capture of an electron to make up for the additional mass, or again, the emission of this positron that is an antimatter particle. And again, positrons can be dangerous in the wrong situation. Finally, gamma rays, which are high energy radiation. They are extremely high energy and they're extremely hard to protect yourself against. So gamma rays can be among the most potentially damaging of any radiation. But we'll talk about that here in the next go round. Okay, so here's our summarization of the types of particles. So we have alpha, beta minus, beta plus, then gamma, and then finally just proton and neutron, just giving you the symbols there so that you're kind of aware of what's going on. And I do usually put, if I have a proton here, for example, just to write out for you, normally you would put that it's a proton plus, and it's a mass number 1, and a atomic number 1. So you would normally put both of those there. And then for neutron, sure enough, it's 1 and 0. That's good. Okay, so sample exercise number 1. I mean, I just showed you the table, so this isn't going to be a big surprise for you, but this is something you want to kind of commit to your memory before the test. So I want the mass number and the charge of each of these types of radiation: alpha particle, the positron, the beta particle, the neutron, and the gamma. So pause the video, try to commit this to your memory, and then when we come back, we'll have the answer for you. Okay, so for an alpha particle, it's a helium nucleus with 2 protons and 2 neutrons. Total mass number of 4. And then without its 2 electrons, that means it has a charge of plus 2. Now, a positron has no mass, just like an electron, but it has a +1 charge, whereas a beta particle, being an electron, has no mass number and a -1 charge. Finally, a neutron just has a mass number of 1 and 0 charge, because of course there's 1 neutron, 0 protons. And finally, a gamma ray has neither a mass number nor a charge, it's just a photon. Okay, so now, this is what's actually kind of important for this chapter, which is what happens when a body is exposed to radiation. This is what we call ionizing radiation. So ionizing radiation is going to hit molecules that are in its path. So, radiation is like a particle, and it's going to hit your body, and it's going to do some kind of damage. If you ingest radiation, it's going to damage your most sensitive cells, which tend to be the ones that are the most rapidly dividing, because the ones that divide the most rapidly require the most resources. So the blood is going to flow there and give more of the radioactive material. So bone marrow, for example, skin, reproductive organs, and cancer cells. This is, the basic idea behind chemotherapy, where if you give radiation to a person who has cancer, the cancer is it's one of the things that cancer does is it pulls in as many resources as it can from the body. And sure enough, in doing so, it pulls in the radioactive material, and then the radioactive material can kill those cells. Normal tissue, since it divides at a slower rate, pulls in fewer of those. But it still is going to get hit with some of them just by nature of its being in your body. Yeah, now of course, your normal tissue can then get damaged by the radiation, and that can then lead to tumors, leukemia, anemia, and other genetic mutations. So the idea is basically radiation can hit your DNA, and in hitting your DNA, it can, either cut parts of the DNA, it can meld parts of the DNA that then can't be replicated. And this can mess up a whole host of things with respect to the body. I know we haven't talked about DNA yet, that's like in the future, but you probably know something about DNA from your previous classes. And as you know, DNA is where the information is stored for the cell. So if you mess up the DNA of a cell, it's not going to have the correct instructions to do everything that it needs to. And that's one of the easy ways that you mess up DNA. Maybe that portion of DNA encodes for something that prevents the cell from growing. Well, if now there's no instruction to say, hey, cell, stop growing when you hit this portion, it's going to keep growing and keep dividing until it becomes a cancer itself. Genetic mutations can occur in germ cells, so in the eggs or in the sperm, and that can then lead to what we call germline mutations, where you can pass that on to your child. Okay, here we go. So here's how you protect yourself from radiation. For alpha particles, literally a sheet of paper will stop an alpha particle, and just your normal clothes. For beta particles, you need a lab coat or gloves. But for gamma rays, you actually need like a lead shield that's very thick, or a thick concrete wall. Otherwise, the gamma rays are too powerful and they will go in there. Of course, the best way to do it is to limit the amount of time that you spend near a radioactive source, and then be as far away as possible from the source. So just kind of a review, alpha particles are stopped by clothing, beta particles are stopped by like a lab coat, so like 2 layers of clothing, and then gamma particles will just go right through you. This is an example of a person working in a nuclear pharmacy, so dispensing a radioactive source. And as you can see, they're working in what's called a glove box here, which has leaded glass shield that will absorb quite a bit of the radiation. And then of course gloves that are also keeping them safe. Okay, yeah, you don't need to memorize this. Just try to remember the shielding type here. Okay, so indicate the type of radiation and protecting for each type. Okay, so yeah, we just did this. So I'll let you do this on your own. Definitely pause the video, come up with your answers, but we did just talk about this. So let's go ahead and keep it moving. Okay, next up, nuclear reactions. So this is the part that's going to be on homework, but not on the test. So nuclear equations, we're going to use the atomic symbols that we've been doing, the isotopic symbols, to show changes in the nucleus in a given nuclear reaction. Okay, so radioactive decay is basically an unstable nucleus that breaks down and emits radiation. And it can emit alpha particles, beta particles, or gamma radiation. Now, a balanced nuclear equation should have the following. The sum of the mass numbers on each side of the equation has to be the same. So for example, if you start with californium-251 and you end up at curium-247, you have to be able to balance that with an alpha particle, which has a mass number of 4. So 4 plus 247 equals 251. That has to be the case no matter what type of equation you're looking at. And then finally, the sum of the atomic numbers on each side has to be the same as well. So californium, again, atomic number 98, decays into curium, number 96. And then to make up the difference, you have an alpha particle, which is, atomic number 2, because it has 2 protons. So 98 equals 96 plus 92 plus 2, perfect. 98 equals 98, 251 equals 251. So yeah, so what we just saw there is that if a radioactive nucleus emits an alpha particle, the nucleus is going to have a mass number decreased by 4 and an atomic number decreased by 2. Okay, so we're going to do an example here. Again, this is only on the homework, so it's not on the test. So we're just going to do this kind of briefly, but it's good to walk it through. So one source of household radiation that you have is in your smoke detector, which is americium 241. So we know that it undergoes alpha decay. So what is it going to decay into? Well, we know that we start from americium 241. So americium, we look it up on the periodic table, that's atomic number 95. We see mass number 241, that's up here. So good, that's what we're starting from. Now, what's on the products? Well, we know it's alpha decay. So that means that we're producing a helium nucleus, which looks like this. We've got helium 4, so that means mass number 4, and helium 2. So then what are we going to do for this part here? Well, we don't know what element it is, right? So we're going to call it element X, and we need the mass number A and the atomic number Z is what we're looking for. So how can we solve for A and Z? Go ahead, give it some thought, and then I'm going to show you how to do it in just a second. So remember, the sum of the mass numbers on the product side has to equal the sum of the mass numbers on the reactant side. So that means that 241 on the left has to equal A plus 4 on the right. Similarly, for our atomic, the Z of the atomic number, we know that those have to equal each other too. So 95 on the left has to equal Z plus 2 on the right. So here, to determine the identity of the atom, we just have to do some simple algebra. So we isolate Z by subtracting 2 from both sides. 95 minus 2 equals 93. Same thing with A, we subtract 4 from both sides for A. 241 minus 4 is 237. Okay, so that's pretty good. Now, how do we determine the identity of element X? Well, we know it already because we know the atomic number Z, right? It's 93. So all we have to do is look it up on the periodic table. Oops, so I guess I could have done that. There you go. It is Neptunium. So the new element has to be Neptunium-237. That's our new isotope here. So that's what happens. And that's how you can do that for any alpha decay. Okay, now beta decay, on the other hand, that's where we're emitting a electron from the nucleus, basically a neutron decays and it forms a proton and an electron, and then the electron is emitted. Now, the math is very similar here because the only difference is our beta particle has 0 for the mass number. So the mass number remains the same, but it has a -1 as its charge number here on the bottom. So you can think of it as mass or atomic number -1. That's going to change the math for us. Okay, so let's say that on the homework we had a question like, write the balanced nuclear equation for the beta decay of yttrium-90. Okay, so yttrium-90 undergoes beta decay. Now what happens? We know it's yttrium-90, so we look it up on the periodic table. That's atomic number 39, mass number 90, and we're emitting a beta particle. So the beta particle looks like this. We have the electron with 0 mass and -1 charge. So how do we find the identity of this element here? Well, it's pretty simple. First off, for the mass number, we have 90 equals the unknown mass number plus 0. Well, plus 0, doesn't do anything, right? So question mark has to equal 90. Okay, now the other part is finding the z of the new atomic number. And for that, what we do is we have 39 equals the missing atomic number -1. Add 1 to both sides. The new atomic number has to be 40. Now, which element matches atomic number 40? Well, we look it up on the periodic table, and that is zirconium. So the answer is zirconium-90, which would be written like this. Zirconium, atomic number 40, mass number 90. Okay, so we'll do this one. Again, I'll have this solved for you on the sample exercise packet key, but this is not going to be on the test. So let's not spend too much time on this here. Okay, positron emission is very similar to beta decay, as we've mentioned, but what happens with the positron emission is you have a +1 charged particle. So that one has effectively a +1 atomic number. Oh, oops. So the resulting nucleus this time is then going to have it's basically one of the protons got turned into a neutron. The mass number remains the same, like here for aluminum-24. You still have magnesium-24 as the result. But what happens is one of those protons goes away, turns into a neutron. So just the atomic number goes down by 1. Gamma emission, we actually have the same. Gamma emission has, it's just a photon. So it's just a pure energy. So there's no atomic number and there's no mass number associated with gamma emission. So what happens is both the atomic number and mass number are the same for just gamma emission. So the classic example is technetium-99m. This is metastable technetium-99. What happens is there's a transition in the nucleus, and that stabilizes to technetium-99 and emits a gamma ray. So nothing changes other than the stability of the internal nucleus. Okay, so here's the summary of those for when you're doing the homework. This chart here will help you out, and this is directly from the book. Okay, so now one problem that we have in medicine is we want to be able to produce radioactive isotopes that are useful, but those radioactive isotopes decay. So how is it that we are able to make our radioactive isotopes? Well, one thing that we can do is if we take two stable nuclei and shoot them together, sometimes we can produce an unstable nucleus that we can then harvest and use for whatever source that we need it for. So for example, when you take boron-10 and bombard it with helium-4, you can produce nitrogen-13, which can then be used for imaging. Don't worry about this. I don't think this is even on the homework here, so let's not even, okay. So that's just one example of how you can produce these radioactive isotopes. Okay, well, and that does it for today's lecture. Again, you can start on the homework now. The key part is being able to identify the different types of radiation for the exam, because that's what's going to come up. And in the next lecture, we'll finish chapter 5, and there'll be a few more nuggets in there on important ways to measure radiation that will become important. So I will see you soon and talk to you then. Bye-bye.